Okay, thank you very much. Thanks to the organizers, especially Barbara, for organizing this, and thank you for letting me speak here. It's great to see people again. So I'm going to talk about deformation, or actually investigating deformation or flow in the mantle with seismological observations. And of course, you've heard a lot already from Jean-Paul earlier and from Anna this morning on using anisotropy to image mantle flow. And that's what I want to get at here as well, but with a slightly different method. And of course, I'm presenting, but most of the work has been done by my PhD students or postdocs, Mo Varizaki and Angelo Pisconti. And also we've worked a lot with Sebastian Merkel and Estelle Ledoux from the Timeless project, and Sebastian talked about this earlier. So the mineral physics has been done by these guys here. So looking at imaging flow in the mantle, I have come up with some questions for this talk. How can we make dynamic processes visible with seismic methods? So can we see convection? And of course, you all know we use anisotropy for that. That is one way. So can the detected anisotropy actually help to understand the processes in the mantle? How important is the knowledge of mineralogy when you look at anisotropy, and how unique are our interpretations? I think this is a really important point in the end. So of course there's lots of different ways of image mantle processes. I'm going to look at flow that creates deformation and that creates anisotropy here. And there was a nice publication from Jean-Paul a while ago where he said that anisotropy is best detected in boundary layers. And this, I think, is very true. So in this talk, we will look at two regions only. We look at the lowermost mantle, D double prime, and we look at the mantle transition zone. The way we use seismic data, or the information that we can extract from seismic data, is mostly by travel times. So we look at relative travel times between different seismic waves. For example, here's the reflection of D double prime. And then we look at travel times between P, PDP, and PCP. What is less often used, but is becoming more popular now, is things like amplitude, polarity, and waveform, and the frequency content. And in this talk, I will actually talk much more about polarity. Amplitude is very, very difficult. And waveforms are very interesting, but here it's mostly polarity that we're looking at. Usually when we look at seismic reflections from the lower mantle, the signals are very small, and we can hardly see them in seismic traces. So what we have to do is we have to increase the signal and reduce the noise. And we do this through stacking. And we, in this array seismology, what we do is we have lots of different stations, and the wave arrives with a certain angle of incidence, so basically a certain slowness at the surface, and we stack along these different slownesses. So if we stack, for example, along this red line here, we will get maximum amplitude for this wave that arrives with that angle of incidence or that slowness. So that would be one of those lines here, or waveforms here. And if we stack along, for example, this blue line here, we have a different one of these lines with a smaller stacked amplitude. What is really important is that we know where the wave comes from. Otherwise, the slowness values that we find here will be wrong and misleading. So we really have to check for that as well. Okay, so we're using these Vespergrams, and you will see them a few times. What's important is that you can distinguish the different waves by their slowness, and you can look at polarities. And even though this is a weird-looking seismogram because it's stacked with a higher order, it's a so-called fourth root stacking, you can still believe the polarities in here. And here you already see that the polarity of this PDP wave going up and down is opposite to that of PCP, which is going down and up. Yeah, and that's going to be important in the coming few slides. But first, getting back at the deformation. So if we have anisotropic material in the earth, such as this olivine crystal here, the picture is from Andrea Tomasi. If we have lots of these anisotropic crystals, but they're randomly oriented, then we still have an isotropic medium. But if they're aligned by, for example, flow, then we have an anisotropic medium. And if we have anisotropic media, if we look at those, and we've heard this before, of course, the velocity will change with direction here. And you can see this here with the slow velocities and the fast velocity in blue, the slow in red. And we can see this for P waves and S waves. So the consequences of anisotropy is that the wave can be polarized and the wave propagates with different speeds and different directions. And Jean-Paul has already talked about shear wave splitting. So you have the S wave going into an anisotropic region and it will be split in the fast and the slow wave. They travel through this anisotropic region, and as they come out, they keep their polarization and also the time difference, because the fast wave traveled, of course, faster than the slow wave. And we can use this to detect anisotropy and also measure anisotropy, in that we, for example, in this case, the SKS wave, and of course we had this yesterday already, the SKS wave should only arrive on the radial component and not on the transverse component, because SKS comes out of the core and converts from a P to an SV wave. If we find signal on the transverse component, it's a sign that there has been anisotropy somewhere on the way. And to measure the anisotropy, we correct or we minimize the energy on the transverse component, and the correction parameters really give a measurement for the anisotropy. And that has been used to look at the upper mantle and the lithosphere, and we use this for SCS waves also on the lower mantle. So if we now come to D double prime and the lower mantle, there has been lots of measurements of anisotropy in the deep earth, and here is, for example, the model by Panning and Romanowicz, looking at anisotropy in the lower mantle. And there's also been a compilation of observations of mostly shear wave splitting observations for D double prime by Andy Nowatzki. And you can see lots of different styles of anisotropy here in this compilation. So sometimes you have SH faster than SV, or SH slower than SV, and Anna talked about this before. But you also have regions where you have very diverse observations. For example, here in the Pacific, where you have everything, apparently. You have tilted anisotropy and so on. Most of these observations have been done with shear wave splitting. And I would like to show you a new approach now that we've been following for a few years now. So the anisotropy that we have here through shear wave splitting, to really constrain the anisotropy, you would need at least 3 crossing paths. That would be really useful to know what we have in there. So we decided that we can also try using, instead of a different path, maybe a different wave. And we're looking at reflections of a discontinuity, in this case, the D double prime discontinuity. What happens is we have the minerals, they align due to mantle flow. So the velocity between the layers will change due to the alignment. So if we go in the upper layer where we have an isotropic material, for example, we have velocities the same in every direction. But if we go in the layer below this one here, where we have aligned or anisotropic material, then we have a velocity v2 that may be smaller than v1 and a velocity v3 that may be larger than v1, because we have fast and slow velocities in there. So if we then look at reflections and reflection coefficients that generate polarities, then we can have one reflection coefficient that generates a downswing upswing in this wave. But if we look perpendicular to that, where the velocity below is larger than the one above, then we have an upswing downswing in this case. Yeah? So we can actually, by looking at different travel directions and looking at the polarities of these waves, say something about the alignment or the anisotropy just below. And in the CREEP project, the ITN CREEP project, my student Angelo Pisconti has actually combined both things. He's used shear wave splitting and reflection polarities. So he's looking at the reflection of D double prime in S waves and P waves, so the polarity of this wave here, and he's also looking at the splitting of SCS, the wave that travels through D double prime. Knowing the reflection polarities and the splitting, and having only one azimuth and a knowledge of deformation, we can then discriminate between different mineralogical scenarios and determine the mantle flow. And I'll show you this in a moment. And that's really useful because we only really need one azimuth, because we have 2 different methods now and 2 different waves. Yeah. So the graphs that you will see in a moment, so what we're doing is we take possible candidates for D double prime mineralogy, and then basically we take the elastic constants from single crystal and textures, and then we have texture, and then basically we can calculate the resulting anisotropy. Using this anisotropy in D double prime, we use isotropic materials above D double prime and calculate the reflection coefficients then in all directions. And what you will see then are these kind of graphs where you have the reflection coefficient for different distances from 60 to 80 degrees. And then in all directions, and the zero direction is the direction of flow. So we have the azimuth relative to the flow. And when it's red, then you can have the reflection coefficient is negative. That means you have opposite polarity of the reflection of the reflected wave compared to PCP and P. And if it's blue, and I have the same problem as Anna, the blue doesn't come out here, but there's blue. If it's blue, then we have the same polarity, so then it will look really like this example up here. So that's for the reflection coefficient for all distances and all directions. And then we also calculate the splitting. And so what you see here is the splitting direction is indicated by these lines here. And the color is, when you have red, there's no splitting, so the delta T is 0. But if you have blue, then you have large splitting time. So that's the splitting time here, and the angle, the splitting direction is shown here. So these are the kind of graphs that you will see. But first we look at the seismic data. We look at the case study in the Atlantic. And so we used as many data as we could get to cover the southern Atlantic in this case. And you see that there are some crossing ray paths. We have lots of different sources here. We have receivers over here. And we find some reflections. We find reflections where PDP has the same polarity as PCP and P. That's the blue points. Then we see reflections where it has opposite polarity, as in this case here. And then we have quite a number of points where we can't detect a reflection of D double prime. And these are shown by these white points here. So one would probably say there is no D double prime discontinuity in this case. We have also got the SDS. So we have reflections in these blue points where they have the same polarity as SCS. And we don't find any opposite polarity SDS. I've not seen any myself at all in no region. And then we find a lot of regions where we don't see any SDS reflections. So no D double prime reflections in S. Looking at the splitting, we have a variety of splitting, but you can see that here they have fairly small delay times, and here they're much larger. And we have a number of those that don't show splitting as well. If we combine this with a previous study in the Central Atlantic, where we also find positive and negative polarities for PDP, for the reflections of D double prime, only positive SDS polarities, and a number of splitting measurements that are binned here in this case, and you can again see the delay time and the direction. If we use this all together and then combine this with the modeling of the reflection coefficient and the splitting, so these graphs that I've shown before. So now I have to go through this. So we have models without the phase transition, so we have isotropic bridgemanite over anisotropic bridgemanite with that slip system here. And I think we really only tried that slip system. Then we have isotropic post-perovskite over anisotropic post-perovskite. And then we have two cases with a phase transition. So we have bridgemanite above and post-perovskite below, but with two different slip systems that we found in the literature. So we used elastic constants that are published in the literature. And then we also try SPO in this case, but we also tried MGO and other candidates. What you can see is that the P-wave reflection coefficient changes between all these different models. And the S-wave reflection coefficient also changes. And the SCS splitting is also different for all these different models because there's different slip systems. So here you have the same slip system, so the SCS splitting is the same. But the reflections change. Yeah? And that's important because you have different observations, different methods. So we then also use these results here and turn basically the anisotropy is then rotated along all three directions as well. Yeah? And then we're trying to fit our observations. And if we look in the central Atlantic here, we can really fit our observations, the PDP reflections, SDS reflections, and especially the splitting directions, not so much the times, with a model that is where the shear plane is turned 36 degrees from the north, and it also has a dip here. And that model that we found here is a Bridgmanite to post-perovskite phase transition, and we have this slip system in here. If we then do this for the other regions in the Atlantic and the LLSVP, we try to fit those together and separately to see which one fits best. And we find that inside the LLSVP, we find, for example, that we need Bridgmanite with the slip system that we try. And it had to be rotated as well, so rotated 75 degrees from north and tilted with 30 degrees. And then we can fit our observations and even the non-observations, even where we didn't have reflections, that fits because the reflection coefficient predicts there will be a very, very, very small reflection in some of these cases. So the non-observations of reflections don't necessarily mean there's no reflector, but maybe there's actually anisotropy and the reflection coefficient doesn't predict any reflection. So putting this all together, we can look at the flow in the mantle from our anisotropy and our modeling of mineral physics here. We can find that outside in the Atlantic there is post-perovskite, and we have the slip system here that fits our observations best. And inside the LLSVP we seem to need Bridgmanite with this slip system here. So, and we also have the tilt and the rotation from north given by the arrows here, so it's the flow direction, and then we have also the tilt down. Outside is not very large, but inside it actually gets larger. So apparently we have some sort of a model where we have flow along the core mantle boundary, which then seems to go up when you reach the LLSVP. And that, interestingly enough, works very well with a recently published paper by Chandler and co-authors, where we have a very similar result here in the slab, or in outside the LLSVP, sorry, that there has to be post-perovskite, and inside the LLSVP there seems to have to be Bridgmanite. This is a different slip system, and we need to try the slip system as well in our calculations. So implications for that is that anisotropy in D double prime allows to image the flow in the lowermost mantle. And when we use splitting and reflections at the same time, we reduce the ambiguity. And we can constrain mineralogy and slip systems with that approach. And the crossing ray paths are not necessarily needed, but of course they can help to constrain the anisotropy better. So we then thought, is this possible to look at that in the mantle transition zone as well? And we use a similar approach, but we're using now underside reflections. So these come as precursors to the wave PP and SS. So we call them P410P and P660P, although I'm only looking at 410 at the moment. And here, in this case, we assume that olivine is aligned, and in the first step, we take Wortsleite as isotropic. And sometimes, and it is going to be a theoretical study to start with, but we have seen opposite polarity precursors to the main phase. So in this case, this is an example from Tibet, and this is an example from the Atlantic. And if you look at, in this case, P-diff, you go up and down, you go up and down, and the precursor, that's this part here, goes down and up. So it's opposite polarity, the same here in this case. So there are instances where you have opposite polarity precursors, something must have happened there. And the graphs that you will see in a moment are slightly different than the ones that I explained before, so I explain those as well. Again, we're looking at reflection coefficients, but this time only for one distance. And what you have is then kind of a line like this, where we have, when we're far away, or when we're very close to this transition between blue and pink, then we have a very small, we have a very small amplitude of the precursor. Whereas if we're far away, we have a large amplitude of the precursor compared to P-diff and PP. If we're in the blue, then we have the same polarity, and if we're in the pink, then we have an opposite polarity. Yeah? So they look slightly different, and here is the example. What we also do, in this case, here we actually look at two deformation styles. We look at axial deformation and at shear deformation. And so here you see now the reflection coefficient for this precursor and for axial deformation. And what you can see for axial deformation, so basically you push down, you can see that the reflection coefficient doesn't really change. It becomes slightly different in amplitude, but nothing that you can determine, or you can't really measure this kind of amplitude change in seismic data, or at least I wouldn't really do it. But there's no variation with azimuth, and that's the important part here. If we then go for shear deformation in this case, then we can see that we do see a variation with azimuth, and in this case for the SH wave. For the P wave reflection coefficient, there is a small variation, but we don't go into positive and negative reflection coefficients. So what we do is we look at different directions, 0, 45, and 90 degrees. That's shown here. So this is the 0 degree, 45, and 90 degree. And you can see that the transition where we go into positive or negative reflection coefficients actually changes here with the angle of incidence that we can translate into the distance. The problem is that this seems to be only for S waves, so we can only see that effect for S waves, and we can only see it for very small distances, which is the large angles of incidence over here. Yeah? But for the distances that we usually use, we don't see that. So what we would have to do is we would have to look at short distance SS and PP precursors, and it seems so that we actually are able to see those even at 60 degrees, where we usually don't look at SS and PP precursors. And this is an example, 60 degrees distance, and we see PP here, and we see an opposite polarity PP precursor from the 410 discontinuity. So apparently the data are there. We just have to now go through all the data and look at that. But in the next step, we started looking at aligned Wadsleite now as well. So instead of isotropic, we now have anisotropic Wadsleite and anisotropic olivine. And that's work that we have done together with the group of Sebastian Merkel, so especially Estelle Ledoux and Movarit Saki. So if we combine the values for the upper mantle, so we use the two different results by Rateron or Tomasi, so that's the blue and the red ones here. And then I also show AK135. So those are for the olivine systems, and for the Wadsleite we use the results from Estelle, and maybe you have seen the poster yesterday. And what you can see here is that, first of all, the P wave now seems to have a polarity reversal at some point, at some incidence angle, which is here in this case 99 or 120 degrees. The S wave shows this anyway, but there's also differences between the different directions. So, and that's for the 35 degree. Sorry, the 65 degree incidence angle, which is a short distance. So you can see these variations in reflection coefficients with distance for the short distances. But for the long distances, the problem is that there doesn't seem to be any variation anymore for the reflection coefficient. So it's the same value no matter in which direction you look. So it's really difficult to then look at anisotropy at the distances where we would really usually look. But what is interesting is that we have opposite polarity precursors here in these long distances or short incidence angles, which seem to agree with seismic data, because we do find these opposite polarity precursors. The other interesting thing is that these new values for the velocity, if we use these values from Estelle together with the values from Andrea and from Ratteron, then they seem to really help to explain the opposite polarity variations that we see in seismic data, and I'll show this in a moment. But first, going back to vertical and horizontal shear, you can actually distinguish between vertical and horizontal shear, but only at the short distance seismic data. And that's a problem because we don't really look at those short distance seismic data. The implications of these results are that, yes, we do have polarity changes with direction for short distance PP and SS precursors, but at larger distances we have no variation of the reflection coefficient, so we can't really use this to determine the anisotropy in a transition zone. But, as I said before, the new results are really useful because they can explain the opposite polarity observations that, for example, Movarit Saki has published in 2019, where we really tried to find a model that can predict this kind of the same polarities for some epicentral distances and then opposite polarity for other epicentral distances. And these kind of new values seem to be able to explain that kind of behavior of polarities. So coming back to my questions at the beginning, can we make dynamic processes visible? Yes, through anisotropy. Can the detected anisotropy help to understand the processes? For the double prime, yes, the slip system and tilt provides a measure of deformation and indicates mantle flow. But for the mantle transition zone, we can distinguish between horizontal and vertical shear, but only with short distance PP and SS precursors, which is still a problem. How important is the knowledge of mineralogy? I guess you just saw it's really important because different mineralogy gives different predictions for splitting and reflections in the double prime, but also for the upper mantle. So it's really, really important to use the correct mineralogy. And how unique are our interpretations? I would say it's okay for the double prime because we use different waves and methods. We combine waves and methods, and that, I think, gets rid of some of the ambiguity. For the mantle transition zone, potentially, yes, for short distances, but we need still crossing paths in this region. So how unique are they really? I think we'll find out in a few years when we have more measurements, more methods combined, and maybe more other models, dynamic models and so on. Thank you.